In this video, we are going to discuss the multivariable chain rule. So let's assume f is a function from Rm to Rn, g is a function from Rn to Rp, and they're both differentiable enough, so assume f is differentiable at a point A in Rm, and g is differentiable at B, which equals f of A, in Rn. Then the composition, g composed with f, is differentiable at A, and the derivative of g composed with f at A is equal to the composition of the two matrices or two linear transformations dg at B multiplied by df at A. So let's do an example. So consider the function f from R2 to R2 given by f of xy equals xy, comma 2x, and the function g from R2 to R3, where g of xy is equal to, let's not use xy for these coordinates. The reason why will become clear momentarily. G of AB is b minus a, and a squared and b. So unfortunately, this is a little bit confusing with the points in the theorem, but in a theorem, a and b are points, are vectors or tuples in Rn and Rm, and here they're elements of R, coordinates of those tuples. Okay, so let's first compute f composed with g and d of f composed with g, and then secondly we'll compute df and dg and multiply them. So, g composed with f, I think I said f composed with g, at xy is g at xy 2x. So now I need to take the second element and subtract the first. Then I need to square the first one. And then finally, I just need to take the second element. Okay, so I want to take the derivative of this thing at xy. And I know that this should be the matrix, which is 2 by 3. So it'll be sort of tall. And the entries should be the partial derivatives of the component functions. So up here, I should take the partial derivative in this box. I should take the partial derivative of the first function with respect to the first variable. So that's going to be 2 minus y. In the second box, I should take the partial derivative of the first function with respect to the second variable. So that'll be negative x. In the second line, I should do the same thing, but for the second function. So this will be 2xy. And then, 2xy squared. And then in the second box of the second line, it'll be 2x squared y. And then finally, I get a 2 here and a 0 here. Okay, so that's my d of the composition at xy. Now let's take d of f and d of g and compose them. So let's do d of f at xy. This is going to be a square matrix, 2 by 2. And in the first box, I should have the derivative of the first function with respect to the first variable. Second box, first function derivative with respect to the second variable. Here in this box, lower left, I'll have derivative of the second function with respect to the first variable, and then second function with respect to second variable. dg at AB, now this one is going to be 2 by 3. So here, I'm going to have derivative of the first function with respect to the first variable, first function with respect to second function with respect to first, second function with respect to second, third function with respect to first, and third function with respect to second. So now what I need to do is I need to compose df and dg and see if I get dg composed with f. And moreover, for a and b, I need to plug in f of xy. So notice that f of xy is xy. Let's go back up. Xy, 2x. So what this is going to be is -1, 1, 2xy, 0, 0, 1. Because instead of a here, I need to plug in xy. And then for df, I have y, x, 2 times 0. And now let's matrix multiply. So what I'll get is a 2 minus y, negative x, 2xy squared, 2x squared y, 2 and 0. And if I look back at what I had earlier, well, they look to be exactly the same. So we're not going to prove the multivariable chain rule in this video. We'll discuss the proof in class. But one consequence that we will prove is if f from Rn to Rn is invertible and differentiable, at a point A, then its inverse is differentiable at f of A, and df inverse at f of A is precisely the inverse of df at A as a matrix or as a linear transformation. So how are we going to prove this? We're going to use the chain rule. So we're going to let I from Rn to Rn denote the identity function. So this just sends points to themselves. And you can check that di at any point x naught is just the n by n identity matrix. So this is 1, and then the rest are zeros. It's an n by n matrix with just ones along the diagonal. So by the chain rule, we know f inverse f at x naught is equal to I at x naught. So we know this because f inverse is f's inverse. And by the chain rule, actually first, before even applying the chain rule, we can say that df inverse f, so f inverse composed with f at x naught should be d of I at x naught. And I apologize, here I had a little d and I should have a big D, which is just the n by n identity. By the chain rule, this is df inverse at f of x naught and multiplied by df at x naught. So we've proved what we wanted to prove. We've proved that these two are equal, which is exactly the same as that. So as a corollary, what this shows is if f is invertible, it has an invertible derivative. Which, you might hope to be true, but is certainly not obvious. And next time, we'll discuss why df being invertible implies that f is invertible, at least locally.